Hello, everyone. Continuing from the previous lesson, we will further discuss the factors influencing the shear viscosity of polymer melts. The addition of additives to polymer melts significantly affects the melt fluidity. For instance, the incorporation of filling and reinforcing materials such as calcium carbonate, red mud, pottery clay, kaolin, carbon black, and short fibers increases the system's viscosity, reduces elasticity, increases hardness and modulus, and worsens fluidity. Another category includes various mineral oils and some oligomers that act as softening and plasticizing materials. Their primary function is to reduce the mutual constraints between macromolecular chains in the material, thereby decreasing the system's viscosity, reducing non-Newtonian behavior, and improving fluidity. During processing, process conditions greatly influence the shear viscosity. First, temperature. As temperature increases, melt viscosity decreases. The reason is that rising temperature increases free volume, enhances molecular chain mobility, weakens intermolecular interactions or the degree of entanglement, reduces the flow unit size, decreases flow resistance, and thus lowers viscosity. In polymer processing, temperature is the primary means of regulating viscosity. When the temperature is above the viscous flow temperature, the relationship between viscosity and temperature can be described by the Arrhenius equation. In this equation, the activation energy for viscous flow is a physical quantity describing the temperature dependence of the material's viscosity. It represents the minimum energy required for a flow unit to overcome the potential barrier and transition from its original position to a nearby vacancy. It reflects the temperature sensitivity of the material's viscosity change. Generally speaking, molecular chains that are rigid, highly polar, or contain large side groups with large chain segment volumes have a higher activation energy for viscous flow. The slope of the line in the graph is steeper. The higher the activation energy for viscous flow, the greater the temperature sensitivity of the viscosity. Such materials are temperature-sensitive materials. For temperature-sensitive materials, increasing the temperature during processing is the method used to adjust fluidity. Examples include polycarbonate, polymethyl methacrylate (PMMA), or organic glass, and polystyrene. When the temperature increases by 50 degrees Celsius, the viscosity decreases by 1 order of magnitude. For flexible molecules, such as polyethylene, polypropylene, and polyoxymethylene, due to their low activation energy, relying solely on raising the temperature to improve fluidity is ineffective. Conversely, excessively increasing the temperature may cause degradation, reducing quality. Therefore, the primary approach is to increase the shear force by applying higher piston pressure or screw rotation speed during injection molding to reduce viscosity and enhance fluidity. The reason is that flexible chains orient easily, making them shear-sensitive materials. The temperature sensitivity of a material's viscosity relates to its processing behavior. For materials with high viscosity temperature sensitivity, as temperature increases, viscosity drops sharply. Thus, raising the temperature is used to lower viscosity, as seen with resins, fibers, and similar materials. On the other hand, due to the high temperature sensitivity, strict temperature control during processing is essential. Otherwise, product quality will be affected. For materials with low viscosity temperature sensitivity, such as rubber, viscosity changes little with temperature. Increasing temperature is not suitable for reducing viscosity here. Industrially, strong shear forces are often applied, or molecular weight is reduced to lower viscosity. However, materials with low temperature sensitivity generally have better processability. They are easier to control during operation, and quality is more stable. Compared to styrene butadiene rubber, SBR, natural rubber has better processability. This is related to the low viscosity temperature sensitivity of natural rubber. The effects of shear rate and shear stress on viscosity. In the first and second Newtonian regions, the melt's viscosity does not change with shear rate. In the pseudoplastic region, the melt's viscosity decreases as the shear rate increases. The extent to which the shear viscosity of various polymer melts changes with shear rate varies. The apparent viscosity of flexible chain polyethylene decreases significantly as the shear rate increases. In contrast, that of rigid chain polymers, like polycarbonate, decreases only slightly. This is because flexible chains can orient easily through chain segment motion, whereas rigid polymer chains have longer chain segments, and the internal frictional resistance encountered during orientation is greater. Consequently, their orientation during flow is limited, and the change in viscosity with shear rate is also small. Materials whose apparent viscosity decreases significantly with increasing shear rate are shear-sensitive materials. In actual production, for rigid chain, temperature-sensitive materials, one should not blindly increase piston pressure or screw rotation speed to enhance fluidity. Instead, the barrel temperature should be raised. For flexible chain, shear-sensitive materials, increasing temperature is not the solution. Rather, increasing piston pressure and screw rotation speed enhances the polymer's fluidity. The effect of shear stress on polymer melt viscosity is similar to that of shear rate. The extent of the effect also varies with the flexibility of the polymer chains. Flexible chain polymers exhibit greater sensitivity than rigid molecules. Regarding the effect of pressure on viscosity, during molding, polymer melts undergo volume contraction due to pressure. Volume reduction increases the interactions between molecular chains, so pressure increases the melt viscosity. For polymer melt flow, an increase in pressure is equivalent to a decrease in temperature. In extruders, injection molding machines, and capillary extrusion rheometers, pressure can reach quite high values. The viscosity increase caused by pressure can be partially offset by viscous heating in the polymer. Moreover, the influence of shear stress on viscosity is significant, and often masks the effect of pressure on viscosity. Therefore, the viscosity increase due to rising pressure is generally not easily noticeable. Let's briefly summarize this section's content. Both increasing temperature and pressure can reduce a material's viscosity, but different materials require different processing methods. For temperature-sensitive materials, raising the temperature is used to improve fluidity. For shear-sensitive materials, increasing the shear rate is the method to enhance fluidity.